Good morning. Can you hear my voice? Hello? Okay. First, still, I try to offer you additional free free experience to try this kind of VR headset, so that if you have never tried to use this kind of VR before, I please try to sign up from these our here, you see, so that you can get some real experience about this kind of headset. So you see, okay, I open additional session for all of you, so that please try to sign up here, right? And then so that this is something I do personally. I do encourage all of you to really understand this kind of very good, this kind of VR. And even actually, I also try to use my project account to see, can buy the HoloLens 2 over this kind of another one made in China, so that's a little bit cheaper. So this HoloLens 2 is about more close to 20 to 30,000 Hong Kong dollar. This one is about 3 to 4,000 Hong Kong dollar. But anyway, it's something, both of this AR, I would say it should be quite good. You see, this AR glass have been go to online crowdsourcing and got this kind of big, this kind of support globally, so that more than like 8 million Hong Kong dollar was raised from internationally. So it's at least from view, it's quite interesting to see this kind of consumer grade thing. Let me quickly show you this guy. This is quite interesting. You have seen this kind of HoloLens 2, right? But how about this guy? It's much cheaper. Well, I will try to buy this. This is cheaper.
？Hi, Ben. How are you doing?
What do you think? This is definitely quite interesting to see another low cost AR glass, right? And it's something I will try to buy this first, and then of course to think about also maybe also try to buy the HoloLens 2 for now for fun. Is for real application. Then design for engineering. I do think it will be quite important to let all the engineering students to understand the potential application of this VR AR MR system for engineering, design, and manufacturing. Okay. Again, so to hopefully again, please try to sign up if you have time. It's coming Saturday, because typically in the weekday I'm so busy on so many projects. Okay. So then now we should go back to our lecture, so that we already briefly mentioned about this another important topic in the building, right? So that this is basically in general for every building, we have this kind of this kind of different type of heat transfer. conduction, convection, radiation, and this is a dominant one. And of course, sometimes but this is another, I would say, important, but it's not the most critical, but still sometimes we need to consider about the phase change, the heat transfer, right? And then so that we will talk about the basic concept of this kind of conduction. For what? For the most important for us is that we need to understand how this one can be impact on this kind of how can we have a more energy efficient building design, right? So that including if you choose right material, right? So that we can minimize heat loss, right? Okay, so that's something I said we are focused on more on engineering application, right? So that once understand the basic heat conduction, that means at least this kind of once a certain material, maybe the wall or window, right? And then if this is a window and this thickness of this window, right? And then the inside the temperature, outside temperature here, and then we can calculate this kind of heat flow rate, right? By this thing, and then the key thing here is related to the K. K is related to the material we use, right? Thermal conductivity and area, how large is area. So these are the most important thing we need to consider, right? The area here, and here is K. So in this case, you can see if we choose, of course, another thing is minus sign here. It is tell us, for example, in the indoor, it's maybe indoor temperature, I would say maybe 20 degrees C, and outdoor it may be 30 degrees C. Right? So in this case, we have delta T. Delta T is what? 30 minus by 20, right? So here we have a 30 minus 20, right? What's 10, right? And then we divide by, you see, the D, right? The thickness of the window and material. So that the minus means the heat flow will most likely come from high temperature to low temperature. So this is something important, minus sign, right? Of course, for engineering design, then we need to consider about those kind of U value. U value is related to this kind of material property of this this kind of thing, and then relate to all this, you can see K and thickness. So this is something important for engineering design of the window or the wall of the building. Okay, so let me show you. I don't know, do you have any questions? So that of course the key thing here will show you, so that the different material, the different K, right, and different U, so that in order to have a much better energy efficient design of the building, we hope we minimize the heat loss, right? Heat loss through this wall and window, so that most likely we prefer have very low this kind of thermal conductivity, right? And typical glass fiber is here very high, and then so that if you have very good this kind of spatial kind of design and material, then you have better this kind of thermal insulation, right? This is related to the we call the thermal insulation. Okay, thermal insulation. Okay, so that thermal insulation means we block heat flow rate, right? If we're air conditioning system in the summer, so that we block heat flow rate. So in this case, we don't try to create some heat loss, right? Heat flow is blocked, so that this is important for HVAC design, right? Be more energy efficient, and of course, eventually, so that typically here, if you have very good design, so then we can now have impact on efficiency, right? Energy efficiency of the building. So this is something quite important for real engineering thing. So that you can see typically if we have this good design and good this kind of design and material used for this window or even smart window, so that we can really have very high increase this energy efficiency. Of course, lighting is another important thing, and then so that is something is important. Of course, as I mentioned, I think before, there's not only look at the passive design of window, right? There's also have some smart material, smart window, so that this is another level. It can become green, right? Using green material for this kind of energy efficient design of the big window, and also smart material becomes smart, this kind of energy efficient window. So this is the different level of this kind of design and this kind of and for the smart building, and then for energy efficiency design. And of course, we also mentioned so that you see traditional window, if only one glass, and then so that in the case you have big heat loss. Okay, so that if you have this kind of double plane, and then you have this kind of thermal conductivity of the air, most likely it's much lower. In the case, it can have a much higher this kind of resistance, thermal resistance, so that heat flow will be blocked. So this is one of important for engineering design. And then of course, as I mentioned, that I think even in Hong Kong, EMSD do set this kind of promote this kind of energy efficient window in Hong Kong, EMSD, right? So that I tell you, if you look at website, EMSD website of Hong Kong government, right? So that they do have set down this kind of spatial energy efficiency office, promote this kind of window, have energy efficient design, air conditioning system. So they do have energy office in it, efficiency office, okay, to promote all these things. But of course, globally, many this kind of countries, they do have this kind of spatial office to promote energy efficiency, right? So that that's something is I think is important, right? So how we can really minimize this kind of energy consumption, and then also minimize this kind of global warming effect, right? So this is reduce carbon footprint. It's a very global issue, right? Okay, now we talk about another. Do you have any question for this heat conduction? We focus on, again, not only just okay, you memorize, but you have to understand the basic concept, and then how we use the kind of thing for the kind of engineering design of the building and building component. The second branch is convection. Convection basically is if you have, for example, we mentioned, right? So that if you have certain kind of maybe most likely we can, for example, you have this kind of pipe for air conditioning system, right? Send the cool air, right? So in here, maybe we say, okay, this is a cool air sent in this kind of piping, air this kind of conditioning, right? Conditioning is pipe, right? So that in this case, then we will describe this kind of heat flow rate relate to the, here we have a TW. This is the wall temperature, and then and also we have T infinity, ambient temperature, so that we can use this kind of thing to estimate the heat flow based on the temperature difference between ambient temperature and wall temperature, and then the heat flow rate relate to H and area. What means okay, so that so this is something and then of course H is we call the heat transfer coefficient, right? And then so that this is something depends on different design of this kind of for example, this pipe for HVAC system depends on material, depends on the temperature difference, right? So that of course we can show you a series of different things, and eventually, again, I will not look into this kind of much more complicated fluid mechanics and heat transfer, right? So that just tell you about a typical value of H, right? For practical engineering, there's actually that it can be very complicated to involve this kind of fluid mechanics heat transfer, and then so that I will not, I'll skip this part and show you what's the typical value of this kind of heat transfer coefficient, right? For free convection, right? For this kind of vertical plate. Vertical plate may be related to the what? The wall of the building wall, right? And then the cylinder may be related to the pipe in air conditioner system, right? And then sphere maybe is a little bit would probably not too common in the building, but definitely this you see depends on now if you have this kind of vertical wall and then air, if you use air actually here, if you use oil, it's much larger, and water is another, it's order of magnitude 100 times much larger than this thing. So what does it mean? That means with different kind of material working fluid, so that we can really adjust the heat flow rate in terms of cooling or heating. So that this is important. So that's why we will, for practical engineering design of this kind of air conditioning system, so that we have to consider about what kind of working liquid or fluid we use, and then have different kind of heat flow rate. Right, the same thing for this kind the design in the cylinder. Right, so this is quite important. And then of course there's also have a forced convection. Forced convection means you have, for example, you have a real electric fan or air conditioning system, and then provide the kind of forced convection of cool air, right, from air conditioning system to every building and every classroom and office, right? So in this case, this is typical value, right? So that for different design and then the different result, right? In terms of this H, okay? So that's something can be used as a way to estimate what's typical heat transfer, right? For this kind of HVAC design in the building, okay? And so of course, typically here I show you, if you want to save energy, the best design probably is you don't use energy, you don't use electricity, and then don't turn off the air conditioning system. Can this possible or not? What do you think? Can we don't turn off air conditioning system? Provide this kind of ventilation. What do you think? This is quite important. So this is related to, can we turn off this kind of forced convection? That means HVAC, in Hong Kong, air conditioning. But still we can have some kind of cooling. What do you think? Can we do it? This depends on your design. Do you think? Depends on the design. We mentioned why basic convection, conduction. So in this case, it's possible we can turn off air conditioning system, but still have some kind of cooling. But you need to have some idea about how to come with a good design. right? So that's why we talk about this kind of a basic principle, right? So if you understand the basic principle, then it's possible you can now really achieve energy efficient design of the building, especially HVAC air conditioning system, or this kind of natural convection, right? So that is something I told you why we want to understand, why we want to come with this kind of understand the very basic principle, right? So that you can really find some better design, which don't use this kind of use minimum energy, right? So here, natural convection. One student said Hong Kong is a population density is very high in Hong Kong, so that also we have so many buildings and heavy building, very tall and very I think the distance between the building in Hong Kong is quite high, so that it's not easy. I understand it's not easy to achieve this kind of passive cooling or through the natural convection, but from my point, it's still possible. Okay, so the one student also mentioned about the issue about those kind of building design in Hong Kong, but from my point of view, it's still possible. You may I can see it's very difficult to completely turn off air conditioning system in typical building in Hong Kong, especially in summer. But if you can try to take advantage of this kind of natural convection, right, to use less energy, I think it's possible. But I think, especially in summer in Hong Kong, the temperature can go to 35 degrees C. And then, but if you have come with a better design of the building, including better, for example, add smart window, energy efficient window, minimize heat loss, block the heat flow rate we mentioned, right? Also, in this case, we can reduce energy consumption of air conditioning system. So this is really possible. And as I told you, like several years ago, I have a project, got this kind of a $10 million project with one MIT, so that I do know that Hong Kong government actually, as one government building, really try to use the kind of smart window in Tuen Mun, the government new government building. They have 10 very, very big kind of the window, smart window. And then actually I helped it's kind of Hong Kong government to do this kind of study about if this kind of 10 smart window can really save energy. Doing that, from my point of view, it's definitely is possible, but how you can block this kind of minimize heat this kind of loss, right, is one of the most important thing from my point of view. So that actually we do have the kind of Tuen Mun government building. They use this kind of a new type of a building, a smart window, so that it's you may also want to look at that the government Tuen Mun government building, it's something, it's government office, and then they have this kind of smart window. So it's something worthwhile for all of you to look at this kind of government building design, so that it's I know probably it's some kind of demo, right? From Hong Kong government point of view, they try to government complex. Okay, so they do have this kind of let me quickly show you this kind of a Tuen Mun government building, so that it's some important I think project from the government side, so that I happen to, because I got $10 million project with MIT, so that I help Hong Kong government to work on this kind, how to evaluate this kind of smart window. So design so that this is a Tunmen government complex building to have 10 this kind of window, smart window, so that you see they show or have this kind of energy efficient design thing, so that this is something I told you is we cannot completely turn off air conditioning for sure in Hong Kong. It's too hot. I don't understand, but how we can save energy? Definitely, this is possible. Okay, at least I told you I do have because USD MIT project, so that the government asked me to help them to do this kind of a study of this kind of the building. Right, do you understand? So it's something it's important for all of you to see that real, right? Real this kind of thing. You may want to go there to take a look about this kind of 10 very large, this kind of smart window in this kind of building, so that I think it should be open now. It's open now, okay? So that you look at this thing. It's because it's government building, so that you can take a look to see about this. Is it's not it should be open now, right? So that at least several years ago, it still undergo this thing, but at least it's some government building design, and then demonstrate how to create the kind of energy efficient design with this kind of 10 smart window. I to tell you there's something it happened. I do have some this kind of special project with help the government to work on this project. So, okay, it's something additional outreach to help the government, because they don't have experience on do research. You know, many government office they don't have do kind of real research. You know, so that at least I supervise MS student, right, to help the government to work on this kind of study about this kind of smart window in this cantonment the building. This is something actually it's free of charge. I didn't charge ask the government to give me money, but it is because I have on the project with MIT, so that I do have a group of this kind of people, right, and then work together so that try to help the government to study this kind of tournament, this kind of government building, right, with this kind of building, and if this can really use, right, how much energy can be saved, do you say? So that is something important, but of course it's also non-trivial, so that for all of you to think about this thing, right? But I just tell you, like I do have some let me quickly show you this thing that it is I tell you how we can really look at this kind of energy design, right? So that once you have a maybe office or building, right, if you have smart window, so how we can do the kind of energy efficient like a study, right? So that we just quickly show you basically based on solar radiation, this kind of open like data from Hong Kong, this kind of observatory, and then we try to look at this kind of solar radiation, and then to look at this kind of window, smart window, used in this particular the government building in Tunmen. Okay, so that this is something based on Hong Kong observatory data, so that we try to do this thing, and then try to study this kind of based on, of course, this is another thing. We use energy plus this kind of free energy like simulation software from Department of Energy from United States, so that you can download, but you can understand the base principle, right? And then try to do this kind of simulation to understand if we can have energy saving. Doing that, I just tell you that I do have some project, and then try to look at this kind of how you can do this kind of energy saving design and simulation, so that of course you can, this is a free. Energy Plus is free, so that you can also download this thing, but you need to understand the basic principle. So that Energy Plus is free. You can download from the US this kind of website. If somehow you want to think this way, because energy saving is one the open source why you can download. But if you understand, you have to understand the basic principle, then you can try to build this kind of model for the office, model for the building, and model for this kind of smart window, and then you can try to evaluate energy efficiency of air conditioning system or whole building, this kind of energy saving. Do you understand? So I just tell you, I have this kind of a big project several years ago, so that I do have a series of peer student, postdoctor, work with MIT, those expert in building technology, and then the Professor Leon Grisman is one of leading expert in this kind of passive design of this kind of building, right? Now, passive design. That's why let me go back to the this particular lecture I was just mentioned, so that the natural convection, so that it is also important topic, right? So, but of course, this is I just give you some very brief introduction, right? So that definitely this is something can be done, okay? And of course, once you have a good this kind of design of this kind of passive design, right? Choose right the window or smart window, or choose material for the wall, right? Material for this kind of wall, and then of course once this one is passive design of the building, and then next one is forced ventilation. So that in the case, this is another important thing, right? So for us engineer, we think, how you can come with this kind of right design of this forced ventilation, including those kind of window type of air conditioning system in your apartment or central air conditioning system. So these are something, of course, I will not talk about too much, but we have additional chapter, right? And of course, one additional thing is radiation. So radiation definitely is another quite important topic. So that, as I mentioned, we have solar radiation, but it's not only limited to solar radiation for our building, this kind of design. So that actually radiation, thermal heat radiation comes from almost every object, including you. Doing that, you have once you, unless you are dead, so you have certain kind of temperature, right? And then so that every this kind of all the body, we have certain temperature. It's not zero temperature, right? Absolute temperature. Then you emit radiation, right? So that of course solar radiation is a much high, this kind of energy source, right? But the human and the wall or window, if a certain high temperature, they have some kind of radiation, heat radiation. So this is important. We need to understand this kind of basic principle, and then how we will come with a good design of the window, good design of the building, and then to consider about this kind of radiation issue. So that this is saying, of course, typically this radiation is an important heat transfer, right? So the heat flow depends on, it's not only that delta T we mentioned for heat convection, it related this kind of temperature of that special kind of surface, maybe the window of the wall, right? And ambient temperature. And the key problem is this related to this kind of thing, temperature to power of 4 exponent. So if the temperature is very high, what happens? So this kind of heat flow really highly depends on this T wall for sure. This is a constant. So that that means that this kind of heat flow will be highly depends on this kind of temperature of the wall surface surface temperature is, for example, the window, right? This is maybe TW, the wall, and T infinity. If it's very high, or it emit a lot of radiation, heat radiation. So that is something, and this is no, it's quite sensitive to the kind of this thing. If you compare with our heat convection, remember heat convection, what was it? It's only, if you still remember, which I mentioned, it's linearly proportional. Heat proportion delta T only. The power is only 1. So do that. So that compare with those kinds of things, so that it's very different. This heat convection we just seen in our previous slide, and this heat radiation, once it's convection, CONV, and this is Q radiation. So it really differ a lot, I would say. Yeah. I don't do any question. I just, you don't need memorize all this, but you understand about how this have impact on our building design, our key component building, right? Window, wall, or air conditioning system. That is an important thing for this thing. And then of course, you see, typically we also, okay, sorry, I forgot to mention. So this also not only relate to the temperature different, and also relate this kind of epsilon. Epsilon relate to the emissivity. I mean, this is related what kind of material you're using, and this kind of sigma is related to the constant, and then area of the window or wall. Okay, so that's something. Then here we should, if you have different material, metal, non-metal, so that this kind of epsilon, why have a big impact on this kind of radiation. You see, if you have aluminum, and then you have this kind of soil or this thing, you can see we differ almost 1 order of difference. So that the what kind of material you are using for the building, a window or other screen material will have a big impact on this kind of radiation. So this is something important, right? And here, of course, you can see, so that you can see if we have right design of this kind of a building, for example, our rooftop, and then if there's some special material coating on the surface of maybe rooftop of the wall, and then we may be able to manipulate this kind of radiation, this energy transfer, right? So that is something is important, right? I mean, if you have that means different material will have impact on this radiation heat transfer, right? So they give you some important thing. Of course, now we look at another thing, heat transfer with phase change. So this is also quite important. So why this is important? Phase change. For example, in a kitchen, what do? You boil the water, right? And then so that but originally is room temperature. You boil water to 100 degrees C, maybe start boiling, right? Produce some bubble, right? Very bubble, so that the boiling heat transfer is a kind of phase change. Or from ice, you heat up and then become solid into liquid water. So this is a phase change. So that phase change has an important energy transfer, especially we have some kind of latent heat. Okay, that means the amount of this kind of energy through this kind of phase change can be much bigger compared with a previous Q heat flow of conduction, convection. Okay, so that this is one another thing. Of course, then we can think about this thing, right? So you can have some kind of impact on, of course, freezing, melting, evaporation, boiling, and condensation. So of course, for our air conditioning system, we most likely use this part, HVAC. But sometimes we still use this, okay? And then, so that we will discuss addition 1 in the following chapter, how to use this kind of heat transfer for design of air conditioning system or HVAC system. And then, of course, building a phase change to have some good application for sure. For example, if we try to use some phase change material, right? So we can come with smart green, this kind of building design, smart green furniture, smart green city, or things. So that something is possible, right? To leverage kind of latent heat, right? So which has a much more energy transfer. Okay, so this is something. Of course, I do have a group of researcher, engineer, try to come with some phase change material, right? For this kind of smart buildings or smart green building design, right? So of course, another phase change is boiling and condensation. I think all of you have seen in the kitchen. Of course, so that for us, we want to think about how we have controllable this kind of boiling condensation for the design of this kind of HVAC system, right? That's the key thing. So that, of course, another thing is, again, we will mention that now I think the government to promote smart or green building design and zero carbon emission design of the building, so that if we can really optimize the design of the building, use much less energy, or passive house. What means if you try to use some better material, one thing, consider about this kind of now we mentioned about this kind of thermal insulation, right? Heat conduction, and then we have leverage kind of additional natural convection, right? And then so that make sure we have choose right material for our window and wall and rooftop. The U value relate to this kind of heat conduction, right? So in this case, if you really try to use right material, right design, so that it's possible to produce this kind of passive, this kind of building, passive house, and so that with natural convection and to achieve this kind of thing, right? But for in Hong Kong, I think it's still difficult to have 100% this kind of passive design for this kind of passive cooling, but it can be used to minimize energy consumption for sure. Okay, and then of course we have come with a series of ways for passive design of this kind of building house, thermal insulation and thermal breeze-free construction, airtight, and a series of this kind of way we can try to produce a better this kind of passive design. And window glazing, I would say if you have, we mentioned here, you have double glazing, right? We mentioned in previous slides, so that in this case, and then here we have air. It's air, right? So that in this case, you can really have better way to engineering the kind of heat loss, doing that minimum heat loss. Okay, and then of course, in general, we want to understand about once you have a passive house design, I mean you have a heat conduction through the window, convection, and then plus additional thing related to the maybe radiation. So that in this case, as mentioned, so that we need to think about this kind of solar radiation issue, right? Solar radiation, solar heating, so that that is something is important. Of course, this kind of thing, as I mentioned, can be done through this kind of, I'll show you, like Energy Plus, those kinds of open source simulation software. So that let me just quickly show you that one, right? So that I do have just quickly show you. You see, if you have this kind of energy build a model for the building, then you try to calculate this kind of based on typical open source data from this kind of Hong Kong observatory, and then you try to calculate the kind of solar heat gain or something, right, as function of time. Do you understand? So this is definitely is something important, solar heat gain, right? So that we can really do this kind of calculation about the thing. But of course, I just tell you this is just give you example. I didn't ask you have to think, but at least this is some important thing related to this kind of how we can understand this kind of energy saving, right, and calculate this kind of solar heat gain, right? And then of course another thing is how can we do you have any question for after now? At least this give you some general understanding about this kind of heat transfer. So I don't know, do you have any question for this particular like topic? Maybe we should have any question. I do encourage some students who got the not very good in the midterm exam to ask question. I don't know if did you look at those your midterm result? I do hope you still have time. If you if you want to get this kind of good result in this this kind of course, for sure, right? You should have study, and then you try to make sure you ask a good question, and then so that then you can at least have some way to improve your final result. And then all of you care about first if you can pass, right? Of course, I don't want to give you a lot of pressure. So this is general education, so that but at least still you need to understand some basic concept in this course, right? And then you try to also do the quiz, and then you try to study, and then you can pass the kind of midterm final. So that I don't know if any question, especially those students who is not doing very good in the midterm exam, or I have to ask you, specific student. Hello? I don't know if who are not very good, the result not good in the midterm exam. Again, I think it's important. I can say so that I don't want to give you a hard time, but at least I want some of you make sure you be more active to ask question, and then so that do that, so that I can give you some help. And also one student asked Yu Tao asked about what is purpose to combine capsule and PCM phase change material. Okay, so that's, let me look at that particular oh, okay, so that the capsule is one. Let me try to look at. Okay, this is a good question. So that you say some of this now maybe involve too much detail. So that basically is in capsule. That means that you try to let me show here. One student asked about this thing. Basically, you see, this is what it means. Phase change material, right? Basically, is what we want to now have. Basically, is people want to increase this kind of energy transfer, so that through by nanomaterial, nanocomposite material. And then in capsule, that means with that means you have many kind of small, maybe micro or nanoparticle and phase change capsule. So that in this case, once you have a much micro and nano, this kind of maybe micro nanoparticle with phase change, what happened? If there's so many kind of nano particle or nano this kind of shell, so that the imposing actually you can increase the surface contact area. So that in case we can, as I mentioned about this heat transfer, all depends on the area, right? In our previous lecture slide, we mentioned about all the Q, heat flow rate related to what? Temperature difference, right? And also they relate to this kind of area. Do you say? So that all the heat transfer, let me quickly relate to these kinds of K or H or something and delta T, change the temperature, so in an area. So in this case, if we can, area is the contact area. So if you can engineer this area, make it into nano. Originally it's like big area. Now we have the nano material, nano composite material. So our surface contact area was much higher. So our area can be much bigger. So in this case, we have a way to increase this kind of energy flow rate. So the Q relate A proportional area, but area can be related to the kind of from micro or to nano material, so that the contact area will be much bigger. So I can really manipulate the kind of energy flow rate. So this is something I think it's a very good question. So that I don't know if at least the question people there's one student who has the purpose to combine capsule and PCM. Again, is the important thing here is let me just make clear. So basically, it's really want to engineering this kind of heat transfer, energy transfer with this kind of contact area surface, right? Once you go into macro scale to micro scale, and then surface contact area will keep increasing. This also we also mentioned this one in our microsensor lecture note. I don't know if you still remember about our lecture note. We discussed about this kind of micro sensor, so that the one section is smaller than surface contact area will be really thin. So the surface really depends on size, right? From macro to micro, or even to nano. So that's why this basically is we want to engineering this kind of micro and nano, this kind of material, and then so that I can really manipulate this kind of heat flow rate. Okay, so this is one additional student as there's one student also mentioning to see effective material. There's one student saying if this facial material they will typically again phase change from my point of view is of course phase change happen from solid to liquid, liquid to vapor. So that what I show here most likely I would say is related to probably is solid to liquid phase change. Of course, there's another one from liquid to vapor. So there's at least two type of phase change, right? Do you say? So this is something I think there's they have different kind of material, facial material for different application. Okay. Then we have one more student asked about the temperature difference will change with time. So how do we know when the temperature inside outside will be equal? one student, Kevin, also asked the question. This question is very important, and the student asks, Kevin asks, the temperature difference will change with time. That is the way we need to understand about how we can engineering this kind of heat transfer for the building. So your question is, do we know when the temperature inside out? Of course, I don't think there will be always equal. Is the temperature inside outside the window or building then is equal, then there's no heat flow. So that in this case, most likely they must have a temperature difference between the indoor and outdoor of the building. Right? So that's why, let me see. So this is a very important question. Let me show you here. You see? Typically, we have in one day, right? Our temperature of the building will be depends on time, right? So in this case, we need to consider about this kind of thing, right? How is it in just like here, right? Depends on in one day, so that most likely it's impossible we will have the temperature inside and outside of the building, the temperature will not be the same. So this show you it's impossible. That's what it's impossible. We can never let the temperature inside outside be the same. Kevin, I don't know, do you understand? So that you see, so basically this is show you, right? So that now in one day we must have this kind of temperature difference, right? Solar heat gain, right? And then so that of course in this case the temperature difference heat gain really depends on the temperature difference and depends a different kind of heat flow rate. That's why we need to engineer design of this kind of window and design. So this is important, as I mentioned, so that we need to engineer the design of this kind of a window and direction of the window, right? And what kind of material, so that different material of the window, smart window, or different direction, you face this kind of thing, then we have very different kind of temperature function of time in one day, or 1 month, or 1 year, and then and then you have different kind of energy efficiency. Okay, so that is something I tell you. Okay, and of course, I don't know if you have any question. So it's good to see that the student ask question. If I understand, if I keep talking and then you keep just listen, don't ask question, then sometimes you cannot digest this kind of material. So it's important for some of you to ask some question. Of course, I still want to ask some student. Chichong Aaron, are you? I don't know if you are online. I need to ask some student more actively. Aaron, are you online? Do you have any question? I do think it's important. I need to be more ask some student. Aaron, are you online now? Do you have any question? Let me see if again we have too many students. I cannot, but at least I do want some student to select student to ask some good question. Oh, another question student wants: when will the second quiz will be held? I already asked both TA to prepare the quiz now, so that most likely it will be probably sometime next week. It's time for you to study, right? Do you understand? So that I already last week I already asked TA to prepare the quiz, so it's time for you to really spend some time to digest what we have discussed right up to now, and then really I don't want over you to wait until last minute. Okay, one day before the exam you start. This is something it's a thing. Yeah. Okay, we have a multiple question. For final exam, most likely will cover all the material from the beginning to the end. But of course, I would say majority of content most likely will the question in the final exam will be most after the material will lecture after the midterm, right? And then one student King Lee asked a question about what PCN, what's the meaning of PCN, phase change material. PCN is phase change material, as I told you why. You can think it's like, for example, water. Water can be a PCN. PCN is a general term, right? Phase change material, right? And PCN, water, it is one very good type of PCN. You know water, right? Water using in our HVAC system. We have a chill water, right? But it's a simple water, but it's not the best material. In the following chapter about air conditioning system, we'll show you if it's water using some additional special material for the air conditioning system, then efficiency will be different. Right? Water is good, but it's not the best one. A good PCN, but it is not the best material, best PCN material. Okay, so that's why we need to engineer and to think about design, engineering design. You say those kind of material, right? Choose right phase change material for air conditioning system, or more general for HVAC system. Okay. Okay, it's good to see student really ask questions, so that I do think it's important to ask some student now be more active to now think. Okay. Okay. Anyway, so that let me see. I should go back to our lecture so that hopefully we can finish this part. So I don't think this and this give you some additional if you ask question, then it'll be easier for you to, it's active learning. If only listen and then you don't think and don't ask question, then your understanding will be different. Okay, so that is something I do think is important for you to ask some question. Okay, now we try to also look at another interesting part, passive cooling for this kind of heat pipe. This is also interesting design, thermal active sealing with this kind of the pipe. So what's this? This is a passive cooling. Actually, this is called the kind of heat pipe. Heat pipe is one special kind of way for cooling with phase change. And heat pipe have been widely used by what? Your laptop computer. It's widely used in in this kind of laptop computer. Do you understand? Why is important? Any idea? Do you have laptop computer? Why will you actually this is a heat pipe actually? Let me show you. This is a heat pipe. So the most commonly used this kind of thing is, it turns out it's not a building. It's actually it's a heat pipe. So almost every laptop computer have heat pipe. Why? One student say quickly reduce heat generated by this kind of huge this kind of heat. Right? You say your laptop computer is very small, compact, and then you cannot add very big like a cooling fan, like your laptop desktop computer, do you understand? You don't want your laptop computer have big cooling fan, right? Do you want to have a so in this case, so that heat pipe actually use almost every laptop computer now because it's much more compact design. Okay, so of course for new smartphone actually those kind of processor, you see, I say iPhone 10, iPhone 12, they have 10 billion transistor, generate a lot of heat, so that actually new smartphone actually also have a micro or mini heat pipe. Okay, so that this, it turns out now is widely used in your consumer electronic, your laptop computer, new smartphone. Your new smartphone have advanced semiconductor technology, and then the problem is just too much heat. So that you say so that's why the cooling, right, of laptop computer and smartphone now they use heat pipe. Do you understand? So that it turns out is a very big problem. Once smaller, this kind of your smartphone has so many transistors in your processor, your computer, CPU, or processor in your smartphone. Wow, you generate too much heat. You definitely need to use the kind of heat pipe to cool down your smartphone or your laptop computer. Otherwise, you burn your smartphone, burn your laptop computer. So it's become, I think, very critical now. Smartphone also have heat pipe now. Okay, so that especially for the most recent model, like I know like Huawei or some new this kind of smartphone, because the processors have generate so much heat, right? So it's if you don't use this kind of miniaturized heat pipe, then you have big trouble. So this become very big problem now for this kind of thing. Do you say it's too much heat now? Okay, so that because for example, Huawei smartphone, they don't call heat pipe, they call what? Vapor, two-dimensional vapor. This kind of there's some special name for cooling. Vapor chamber now for they don't use this kind of special name in this kind of our thermal engineering, but they do use this kind of advanced this kind of cooling or for this thing. Let me just quickly show you the smartphone, the heat pipe. It is let me show you about at least I do think that many of you have new smartphone, and then so that some smartphone really has you see. Anyway, sorry, this is the one like now, for example, Huawei use a kind of vapor, like a special vapor chamber for cooling. Actually, this is a miniaturized heat pipe because it generates too much heat and some special material, right? Graphene is thermal conductivity, like which is K, right? It's much higher, so it can easily dissipate the heat. So that the new advanced smartphone, they have to use the kind of miniaturized heat pipe to cool down your smartphone. Otherwise, you too much heat. This become one of the big problem now, right? So okay, so now we have one student who has a question about one student asked about copper vacuum chamber. For typical PC or desktop computer, most likely they have what? Big heat sink and cooling fan. So of course I can see depends, right? Some of PC may be also considered about using the heat pipe, but most likely this kind of heat pipe may be more expensive. So that because desktop computer can be a large area, large size, so that they can get kind of the kind of big heat sink and the cooling fan. Do you say? So that do you say if you heat pipe most likely for is more expensive. So that if you can see, if you look at those kind of desktop computer, those cooling fan, do you say usually it's very big heat sink and cooling fan. So you know that is much cheaper. If you use heat pipe, in general, it would be much more expensive, I would say. I just show you typical those your computer. Why your computer usually has this kind of this, let me show here. You see, this is much cheaper. If you use a heat pipe, in terms of cost effectiveness, since I think majority of the PC of that computer still use this kind of heat sink with cooling fan. And some of high-end computer PC, they using the liquid cooling. Liquid cooling, and so in this case, they have a what? It can have a generally this is the fan has a problem. What's the problem of the fan? Too noisy. Too noisy is that? If it's so high-end PC or that computer, if they want a very quiet environment, they have it could cool. Why? Really cool. It's not PC. It's not heat pipe. It be cool, and then it can be quiet. So it depends. Yeah. One student asked, I think typically it really depends, right? Because heat pipe it need much more engineering design manufacturing, so that the most heat pipe was made by what? Japanese company, and also some company in Taiwan. So that in general, if you look at the typical heat sink and those kind of cooling fan, most likely in like Shenzhen or this kind of this area, right? Greater Bay Area, there's many company. It's low end, but heat pipe it's require a lot more engineering. Because I know that in this area, Shenzhen or some company also creates this kind of heat pipe or for this kind of a laptop computer or smartphone. But it's in terms of technology, in terms of thing, it's more high end, so that the majority of heat pipe for laptop computer most likely is made by a series of company in Japan and some company in Taiwan. I tell you, so that Chen Tong, you say why so expensive? It's technology. Just like why Shenzhen or China have import 200 billion, 300 billion semiconductor chip. That is a technology, huh? Because it's not easy to build advanced this kind of semiconductor chip, including this heat pipe, very compact, high performance heat pipe, most likely made by the company in Japan, high end. I tell you, I can give you a list of company because I know the Japanese. 30 years ago, I studied 3 years Japanese. When I do research, I also try to study things, so that the heat pipe, majority of the laptop computer heat pipe actually most likely is made dominant by those companies in Japan and some company in Taiwan. Okay. Any other question? Okay, very good. So to see that we have some more question is important. I do think it's important for all of you to really ask good question and then try to not just listen, right? So that if you just listen and then you don't think through, then it would be thing. Okay, so another thing is of course we mentioned in the first one, so that in the building, right? Orientation of the building now will have impact about this cooling, right? Traditional, like in Chinese, this kind of many years ago, 1,000 years ago, we already tried to think about how we try to have buy those kind of apartment or building about they were facing this kind of a thing, right? North and south. So that's the reason. In terms of solar heat gain, we mentioned in our previous slide, so that the different kind of orientation, the solar heat gain, a function of time in one day will be different. so that this is structural measure, right? Doing that, and then of course air tightness. That's the thing. For commercial building, we have central air conditioning system like our UST building, and then air tightness as another thing. You don't want to have the leakage of a cool air, right? And then so there's a serious thing, and thermal breach, and the serious thing is important in terms of this kind of design of building and orientation and material, right? And of course, another thing is sometimes solar, right, radiation is bad, sometimes it's good. So if you have a good design, we allow this kind of solar radiation to replace the lighting, right? So that this is something is another level of engineering. If we can try to have a better this kind of design of rooftop and see allow solar radiation to provide the lighting, so we can minimize energy consumption of this for all the lighting, right, of the building. So this is another kind of important thing. Okay. Anyway, I understand that I will not ask you to look at too much about this kind of calculation, but at least I just show you they do have a free open source software you can download from this the US government website, so that you can download and then to Energy Plus and then to calculate this kind of solar heat gain, so that this is something you can download, right? This thing, so that I just give you things, so that if you want to look at more quantitative thing, then you may want to download this kind of a free software, right? So that if some of you want really to understand more and then try to think, so that I would not ask you to about a lot of kind of calculation in the exam, but instead I hope you can understand the basic concept of this kind of heat transfer, right, for our energy efficient building design and how we can save energy. I think this is one important thing, right? And so again, solar heat gain is important, as I mentioned, for how we can evaluate this kind of energy saving. Like we just show you about this kind of my project. I help this kind of Hong Kong government, right, to evaluate this kind of smart window in Twin government building, right? So that we need to calculate, right, based on this kind of energy simulation software, right, and based on those kind of typical temperature data in one day or in 1 month or 1 year, so that we try to also we need to also enter typical material property of the window, and then so once enter our material, and then we can calculate the kind of heat flow, solar gain, and thermal radiation, and then look at heat gain doing that. So this is something is can be done by using this kind of free software, so that I understand all of you prefer free, you don't want to buy. So this is not any product, but you need to understand basic principle, then you can use this kind of free software for this kind of understanding of design. Yeah. And of course, you see, when we look at this kind of heat gain, or look at energy efficiency of the building and or window or thing, then of course there's another thing is we also may need to consider about if this kind of window is transparent, opaque, or something, right? Of course, or smart window is depends on the temperature of the window, and this kind of optical transparency depends on. So it depends on what kind of material you use, right? A traditional window, that the optical property is fixed, but if it's smart window, like a thermochromic smart window we show you in this kind of government building, then it's that optical property will be function of temperature, a function of temperature. So this is something function of temperature or the window temperature. Then this in this case, we call we can really have better way to control the solar radiation, right? Achieve energy saving. So this is something is this smart window has their advantage, right? No, this is something I tell you this important for you to understand. Of course, this calculation can be very complicated. I got the expert, the postdoctor, to do the kind of analysis about smart window, seeing and then can use this energy plus to do calculation. This even smart window, you need to think about how to build this kind of model in Energy Plus. So that I just skip this part and just give you some basic understanding about this importance of this kind of. I think the concept is more important thing. Okay, so for this course, okay, again, so that in general we have different the kind of like design of the kind of passive design of this kind of thing. Passive heating and passive cooling really depends on how you engineering the design, right? So that then that's it. Okay. Anyway, so finally, of course, when we look at energy saving for the building, and then of course it's about location. Okay, I think we sorry, I also run out of time today. So do you have any question? Any question? It's good today. So at least a series of questions. If you have more questions, please feel free to ask questions on camera side, especially those students who have not do very well in the midterm exam. I do encourage ask questions on Canvas. Again, I do hope some of you take advantage of the free this kind of session to try this kind of VR for free. Okay, if you want to sing, I try to sign up on this doodle. Okay, so that okay. Any other question, please ask question on the our website. Okay.